All right. So my name is Grant Boykin, a fellow organizer here at DevOps Days, and I just wanted to thank everybody for joining us on day 2. We had a bit of a logistical issue with the speaker, but we have a replacement. So I have Skyler and Bharath that are going to come up here and give you all a talk. And I'll let them introduce their talk name because it's really long. But yeah, please welcome them. They pulled in last minute, so please, a round of applause for Skyler and Bharath. Come on up. You should see it on the monitor up here. Do they see the slides? Okay. They don't see the slides. There we go. You're good to go.
Hello. Okay. All right. Hello, everyone. I'm Skyler. I work for Capital One as a software engineer. And recently, we worked on a GraphQL subscription service for real-time eventing, and that's what I'll be covering today. So let's get started. Here's a little bit of what I'll be covering. Basically, I'm going to cover real-time data delivery techniques, the advantages of using them, how we've kind of implemented it and how other companies have, and the advantages and scalability of swapping to event-based architecture. So let's begin by defining and understanding what real-time data delivery is and a little bit about what it entails. So real-time data delivery has become a very big thing recently, especially with the rise of microservices and things such as Redis, PubSub models, Kafka, and as a subset of that, GraphQL subscriptions. So event-driven architecture delivers minimal latency because it's basically pushing the events in real time. And this continuous flow of events is a huge thing in today's society of basically get information to the customers as quickly as possible. And a huge advantage of that is the ability to scale it without any sort of batch processing or polling mechanisms. So as a part of that, I think a large aspect of being able to respond as quickly as possible is what's driving event-driven architectures. The ability to make faster decisions in the market, or the ability to automate processes as you respond to things in real time, as well as risk management. So the ability to respond to things such as CPU utilization, or maybe security vulnerabilities, anything you would want to respond to quicker is going to be a subset of swapping to this kind of process. The ability to reduce the delays to respond to any sort of event, or to optimize your resource utilization by only responding when necessary is a huge driving aspect of why we and many others have decided to swap to this style of architecture. So here's kind of a breakdown of the technique difference between traditional polling and pushing. Based on so let's start with a mechanism, which is for any polling style architecture, you're going to have something where it is based on a request response model. So the client repeatedly requests updates, and then you get a one-to-one response with that. Versus pushing, where everything will be driven by the server-sent events. So you're only responding when necessary, and you're responding based on what happened, as opposed to the traditional model of, I'm going to request data and get whatever you have available. For latency, your polling is going to be completely dictated by whatever your interval is. So you're always going to have that trade-off of, well, if I make a shorter interval, I'm going to get data back quicker. But obviously, you're going to trade that off for resources, because as you pull more and more, your server is getting more and more requests where there might not even be data available. Whereas with pushing, you're getting data exactly when it's available. There is minimal latency because it's just going directly to your client. And then efficiency, as I kind of mentioned, polling is very inefficient from a server perspective. You are not utilizing the resources you have available because you are just polling arbitrarily, like whatever your set interval is, whereas with pushing, it's responding in real time. The complexity, though, is where you kind of see the bigger differences because traditional polling mechanisms are very, very simple to implement. I mean, HTTP has been a driving factor for many things, as well as REST, to just be able to set up a very simple HTTP request and get data back on a set interval is very simple. Whereas once you introduce pushing, there's a lot of considerations that kind of come in as part of that. Managing the connections, keeping live connections open, as well as different protocols depending on if you use WebSockets versus something like SSE, which is HTTP-based. And then as for the use cases, I don't want to make it sound like push-based is the only solution. It is just an option. There's still plenty of times where maybe polling does make sense, whether that be through browser limitations, or maybe the polling interval is large enough where it just makes sense for the simplicity to just poll as opposed to push. Whereas if you have something like a chat application or live notifications, it makes much more sense to do a push-based process. So, inefficiencies of REST for real-time communications. Like I mentioned, REST has been around for a long time. It's well developed, but it does come with the traditional limitations, right? You have the request-response model, which doesn't allow for you to request dynamically. So what I mean by that is when you want to swap to something that is, say, like push-based, you're able to choose how you receive those events and what drives those events. So you can basically choose to dynamically send different sources or different availability notifications just based on whatever you want, as opposed to with a client, you're fixed on whatever data the client wants to request. High latency, as I previously mentioned, you're going to have to choose a trade-off whenever you go like with a REST-based model, because if your polling interval is too large, you're not going to receive that data in an efficient enough time frame. And if your polling interval is too short, you're going to have the issue of basically overloading your server or scaling that out for future requests. And then not being event-driven for REST is going to basically limit you in essentially the application usages, as I mentioned previously, live notifications, things like that, chat features. It's just not going to be available if you stick with a traditional REST model. So now let me discuss a bit more about the different techniques that kind of filter down further on polling and push-based processes. So here are the traditional 4 processes that people will use to kind of implement these processes. As I previously mentioned, they all kind of have their pros and cons, so it really just depends on what your situation is for when you choose to do this, and also to consider whatever your server resources is and how you want your architecture to kind of look going forward. So starting with short polling, that is basically the simplest way to implement any sort of response-driven architecture. You basically set a basic interval process, and you just poll that regardless of what the outcome is. So you make a request, you get a response. Whether or not there's data, it doesn't care. It's very simple to implement, but the trade-off is, again, your server is going to have to process all those requests. So scalability becomes a major issue. As you start getting hundreds of thousands of users, you have a lot of empty requests that really aren't doing anything. Long polling kind of builds on top of that in a way to allow it so that it will only respond whenever there's data available. So you're limiting the amount, but it is still opening and closing a constant connection, which is not optimal. And on top of that, once you start introducing things like load balancers, you start running into time limits there, where if no data is available in, say, a minute, your connection can close, which, again, further makes a constraint on the way you're able to utilize your resources. WebSockets is the first one we kind of get into where now we're swapping to push-based. WebSockets is full duplex, so two-way communication, very common for things like chat apps. You will basically open a TCP connection, and then once you've done that, that connection stays open, keeps heartbeat events to bypass the limitations of traditional ALBs, and will send and receive data, as well as have the flexibility for binary data as well as text-based data. The cons of that are there is a special protocol for WebSockets, which builds on top of a HTTP handshake. So once you have authentication and authorization built into that, it is much more difficult to be able to monitor the traffic going over that open connection, which is where server-sent events comes in. So server-sent events is one directional. As the name implies, it comes from the server to the client. And it is built fully on the HTTP protocol. So there is no upgrade of the connection special for this. You're just able to make a traditional HTTP request, which never closes. And then if you introduce things like heartbeats, you never have to worry about the load balancer closing that connection or swapping. The trade-off being it is one-way communication compared to, say, WebSockets, where you're able to send and receive data. You will only be able to receive data here, and it is text-based only. So here is just a further breakdown of basically SSE versus WebSockets, the two push-based protocols that we talked about. I've covered most of this, but essentially, server-sent events is going to be your one-way communication based on HTTP. And then WebSockets will be bidirectional, but it will be based on its own protocol once you have that initial handshake made. So now let's talk a little bit about GraphQL and GraphQL subscriptions and how those fit into this, and then how we kind of utilize them and how other companies are utilizing them. So let's start with what GraphQL actually is. So GraphQL is a query and runtime language. As the name implies, it is graph-based. So what I mean by that is you are able to implement it with multiple resources on the back end, and it abstracts that away to send you only the relevant data requested. So compared to, say, REST, a traditional response, you can kind of see in the graphic here that this will send you only the data that you requested. So let's talk about like some of the key benefits and why that's important. So sending only the data you requested is a huge aspect of GraphQL because it's going to limit the amount of data you're sending over the line and fix the issue of what if I want specific fields and I don't want to overfetch or underfetch any data. This becomes even more important once we start talking about push-based notifications where that is also dynamic in nature. Another important aspect of it is the ability to basically define everything within the schema itself. So defining contracts and things such as that will be built into the API itself, as opposed to REST, where it's very easy to have contract drift or situations where you are no longer in sync with what your documentation says it is. So with this, it is almost self-driven by the documentation itself because the schema is going to define what the client is able to request and the data they're able to see. And with that, you get enhanced performance. So as you scale out further and further and you start introducing more and more events, you're starting to have a lot more data that you have to process. By introducing GraphQL there, you're able to limit it a lot more by basically only responding with the data that the client is interested in, whereas with REST, you're going to have that issue where you either need to make your contract very, very broad to accompany all the potential changes, or have to introduce more endpoints or other things to account for different events. It doesn't scale in the same dynamic nature as this, which overall just leads to a better user experience. It's going to be faster, and it's going to be dictated purely by whatever their customization or experience is. And then further, what is GraphQL subscriptions? So subscriptions are a feature of GraphQL. Basically, it has its own mechanism that implements push-based processes completely built in. So what I mean by that is you can define within your schema a subscription, and once you've done that, it is able to process either WebSockets or SSE based on what you want. And this is a huge win from an architecture perspective, because now you don't have to set up completely separate applications for processing your real-time events. What I mean by that is traditionally WebSocket servers are a lot to basically build up, or with SSE, building up an entirely separate application just to process real-time events is a huge ask, whereas with GraphQL, you're able to do that all in one. So let's talk a bit more about those exact benefits. So as I previously mentioned, the schema for GraphQL is dynamic, so there is no overfetching or underfetching. And as a part of that, it works perfectly with the dynamic nature of push-based events. So by having all of this in a single application driven by a single schema and not having a separate application, you're going to avoid the code drift problem of having, say, your static data driven by one API and then having your event-based data driven by another. It's all going to be in a single location driven by a single endpoint, and it's going to scale based on whatever your needs are or the limitations of the server. So that's going to maximize your reuse of the logic, all having it in one. You're not going to have to set up a separate authentication service or anything specifically just to do your real-time flow. And all the logic for processing tends to be very similar. What I mean by that is normally when you fetch static data or when you get event-driven data, you're going to want to process that in a similar way. And by having that all consolidated within one application, you don't have to worry about those two processes drifting or having to re-implement certain things. Another big aspect of it is the client-driven data selection. So this kind of plays into the schema I mentioned before, and that one use case we came across is that the client side needed a lot of customizations. They needed to have their data driven purely by whatever their specific needs were. And as I mentioned with REST, that's very difficult to do. Like you're looking at either making custom endpoints or having a very vague, not very descriptive endpoint that basically encompasses all the different potential combinations. Whereas with GraphQL and subscriptions, you're able to basically define the schema just based on whatever the client's requesting. So if the client only wants very specific data as a subset of the event, you're able to deliver that to them in the most optimal way possible. So now let's talk a bit more about the specific use cases like I've come across with GraphQL and how other companies are kind of implementing that. So a big one is Shopify with their Black Friday, Cyber Monday live map. So this architecture kind of illustrates a lot of the potential of GraphQL subscriptions and how it's being used at scale. Basically, they were processing millions of events and showing it on a dashboard of real-time updates of every sale or transaction. And starting from their Flink cluster of processing millions of analytics, they were able to deliver that event to the UI in sub 1 second. None of this would have been possible with any sort of polling mechanism, especially at this scale, because you just have too many events, and the scalability of the server is just not going to be able to handle any dead data. So here, you're able to see that once they send it to Kafka for the microservice architecture and then go to their SSE server, from there, they just have a GraphQL subscription that basically sends the data to the client in real time. And even just based on this diagram, you can kind of see how having that SSE server implemented like off of the Kafka topics is pretty minimal architecture for being able to deliver sub 1 second response time for millions of events. And now Amazon Music is also using GraphQL subscriptions. However, they aren't using SSE. They're using the other push service that I talked about, WebSockets, to deliver two-way communication. And theirs is driven through AppSync. So from a maintenance and scalability perspective, This is a fully managed service that they have for GraphQL and GraphQL subscriptions, as well as, I believe, Redis PubSub. So for this, you actually have to do minimal effort to set up any of the architecture. They handle all of that for you, and it delivers two-way communications, whereas with the previous example, that was one-way deliverability because of SSE. So with this, they tend to use it for real-time song updates, as well as collaborative features such as voting, to be able to deliver the most real-time experience possible with two-way communication. And with that, I'll pass it over to Bharath, who's going to talk a bit more about the challenges as well as the lower-level implementations.
Can you hear me? Okay. Thank you, Skyler. I'm Bharath Chekuri. I'm actually a senior lead software engineer from Capital One. As you have seen, actually, Skyler was explaining actually how did we implement this real-time system where we were able to send the events very quickly as soon as there is an updates to that specific data. But obviously, it comes with like a lot of challenges. Some of the challenges which we have encountered, I'm going to talk about like some of the high-level challenges which we have encountered, and then how did we overcome those challenges during the implementation of the system. So obviously, when we are using SSE or WebSockets, explicitly in our use case, we used SSE. We need to maintain lots and lots of connection. In our use case, we had to maintain like at least like thousands of connections to the backend system. Obviously, opening those many connections required a lot of resources, and we need to make sure that we have a proper resourcing allocation for each connection so that we will be able to support lots and lots of connections and able to send the real-time data to them. And another important aspect actually in this implementation is actually data consistency, because we are sending the data as we see updates quickly to the UI. So we just want to make sure that we send the right data in a right order. That was one of the challenge which we have encountered while we are implementing the system. And another important thing is also back pressure and flooding. So when we use actually some kind of like any kind of real-time systems using like Kafka or like SSE or like all these technologies, right? So we need to make sure that we basically able to handle the back pressure and flooding is very properly. What happens is, right, let's say if there is let's take an example here, like so there's a user who is actually waiting for a data, and we basically started actually updating that specific data from the backend from various streams. Now we're going to flood that user with lots and lots of events actually, and then his UI keep refreshing, and you'll get frustrated. We just want to make sure that we handle them properly, and at the same time back pressure. We don't want to also delay the events which is actually going to the user. Otherwise, then it actually becomes like stale data. The last but not least is a very important one: error handling, recovery, and security. So we used a GraphQL here. The GraphQL has actually a, it always like sends 200 response, even if you have some errors, like if you don't have data, because it actually connects to multiple sources of data. So, and at the same time, we need to authenticate the user, make sure that the user is actually authenticated successfully. And because we are connecting to a user from the server side, we need to make sure that we actually maintain that connection properly without losing it and sending the data to that user, without actually having any issues with respect to the losing connections. So those are the important things which we have actually encountered. Those are some of the significant challenges which we have encountered actually during the implementation of the system. Let's go and deep dive into some of the best practices and implementation considerations which we have chosen during this implementation of the system, so that way we were able to support all these use cases to the customer. Yeah, so we have divided this section, in this implementation section, into two major parts actually. One is optimizing the data delivery. The other piece is actually going to be handling the scalability, like the performance of like thousands of events coming in. So in the optimization of the data delivery, so the key things which we have highlighted here is actually like filter the subscriptions and batch updates and use lightweight payloads. I don't think that these terminologies is like is like a complex things to understand, but I'll go a little bit deeper into like each one a little bit. So the filter subscription, it actually plays a very important role for the security point of view, and also to make sure that we actually send the right data to the right user. Let's say we have like thousands of connections coming from like various browsers, various users who's authenticated to our system, and we don't want to push every update which is coming to our server to all the browsers actually. So we want to basically like filter them using their user context, their filter criteria, their entire context needs to be considered before we send the data to the UI, so that way we are only sending that specific user context data to that specific user. And batch updates, we talked about this back pressure and flooding, right? So the batch updates is the one technique which we have used it to solve this problem. So we actually receive like lots of events actually. We used a Kafka here. So Kafka is actually very scalable, and it actually produces like the data change. It can scale to like whatever the level we wanted to. So we are receiving like a lot of updates coming in. So what we do is, right, in the server side, we basically try to batch it as small batches as possible without having like major latency to the UI in the data delivery. So that way, so if the events are coming actually for that specific user, we try to batch some of the requests coming in, and then we basically send that back to the UI. So that way, UI can actually take the batch context and then update the state. So the last one is actually the light payloads. So it's actually important. It actually adds a little bit of extra work, because the moment we say light payloads, now UI need to manage the proper states, make sure that we only update the data which is actually coming in through server-side eventings. But it actually going to help actually a lot, because your UI threads are actually kind of like, let's say if you're loading an initial page and you started actually pushing like lots of data, kilobytes of data to UI, and UI is actually kind of like struggles to render that data, because you're basically trying to push like lots of data. So that's why we kind of actually leveraged actually kind of like only to send a delta updates. So saying that, let's say we have 10 records came in, we will only send updates which are actually got updated, like that specific 10 records. So we don't send that entire payload, so that we are burdening the UI, because most of the UIs actually kind of struggles if we send like lots and lots of data. Yeah, so that was the image, sorry. So obviously the next important aspect here is like handling, like a scaling and performance, right? The main goal is actually of like this real-time system is actually delivering the data very quickly, but we need to make sure that our infrastructure and our performance of the events delivery is actually much faster, so that we can actually able to handle like lots of connections, and at the same time, the user experience is actually much better. So we used actually Kafka. So we used a Kafka pub/sub model. Like, so basically, like all the events comes in from various streams. We consolidate all of them, and we basically publish it to Kafka stream. And there is the server. We call it as a BFF, which is actually GraphQL BFF, backend for front end. So that actually going to listen to all the events coming in from the various sources, and it actually does all the user context filtering, everything which we discussed in the previous slides, and we send it to the UI. And the next one is actually like horizontal scaling. It is like, I mean, it's again like, you know, it's a very simple term, but we actually implemented actually, like, you know, in Capital One, like we leverage actually AWS, and then most of you might already know, but so with AWS, like we basically used ECS Fargate fronted with, like, you know, load balancers, just to make sure that, you know, we were able to scale lots and lots of connections. We were able to support lots of connections, and at the same time, we were able to send the data very quickly. Last one is very important thing, you know, proactive connection management. So it could be possible that, you know, the users can actually open like lots and lots of tabs, and then you could actually have like so many SSE connections. It is very important to maintain actually like you know, write connections and remove unwanted connections, so that we don't actually have all those unwanted connections with us, and then have our like CPU or like memory usage goes up very high, and then the containers keep actually rebooting, and then they're kind of keep auto scaling actually. So kind of we leveraged actually a limits. We implemented actually a connection limits like per user, you know, per session. That way, you know, we don't accept like more than that connections. And at the same time, we kind of also do publish heartbeat events. And if the heartbeat events is actually not going through, then we basically detect that that connection is actually stale connection. We will basically go and then delete actually from our connection pool, so that we don't actually keep those connections actually from within ourselves actually. With that, we are actually open for Q&A. Any questions? I'm sorry, you know, Skyler, you want to come here? Okay.